Perfect, and we're back. Welcome back, ladies and gentlemen, to more math from room 1430. Today, I need to teach you a whole bunch of stuff. It's about vectors, of course. And if we take a vector like this vector, 2, 1. Ooh, that's a difficult vector. It goes over 2 and up 1, right? Right. Then let's say I told you that it's different if it was here or here. Like, even if, here, I'll clone them so you can know that I'm talking about the same exact vector. You've always known down deep that these are different. And I kept saying, oh, it's the same direction, same magnitude. And so therefore they're the same. Well, they are the same in one way, but obviously they're in a different place, and therefore they must be different. So how do you tell that they're different? You tell where they started. It's like, here's this vector, but I'm going to start it at 0, 6. And then here's this other vector, and I'm going to start it at 0, 0. All right, so I want to say, let's make something more interesting than 0, 0. Let's say this one starts at 1, 6. That spot right there is 1, 6. And this spot over here is going to be like 7, 3. That's where both of these vectors start. Then watch the difference in what their equation vector is. Their equation vector goes like this. 1, 6, x, y, plus lambda. And then this was over 3 up 1. What just happened? I just wrote that vector in an equation. It's not that bad. Watch me write this vector. It's starting at a different place, right? But it's still going the same over and up. And so watch. X, y. Oh, that's terrible. I'm going to try that again. X, y is, notice starting point, 7, 3. Gotta move it over so I got more room to write. Plus, anyone want to take a guess at what I'm going to write next? Close. What's that little thing in front of it? That's called lambda. Lambda 3, 1. Look at that. Aren't they pretty much the same thing except what? What's different? Starts here versus starts here. They start at different spots. Yes. What is a lambda? It's a variable, and it's Greek. It's kind of like an x or a y. It's just a variable. It's a lambda. You just haven't seen that one before. Have you seen alpha before? Have you seen beta? Well, meet its crazy sister lambda. Okay, so let's do another one. This time, I would recommend you get a nice piece of graph paper, and let's just get a piece of graph paper up. You can get that in many different ways. Insert a sticky that's got graph paper on it, or open a page that's got graph paper, but get some graph paper. What if I said, we're going to start here, and we're going to go over 4 and up 1. Now, in before, I would always say that's the same as that. And it is, kind of, because it's going the same direction, and it has the same magnitude. That's true. So therefore, it's got the same direction, same magnitude. Those are the two key things about a vector. Well, what's the difference then? Well, obviously, if you start them at different places, they're going to be in different places. So we can make an equation for that. So if you caught what I was just saying before, in case you're having a hard time reading the thingies, this is at 1, 2, and that vector is going 4 in the I direction, plus it's going 1 in the J direction. Would you write me an equation for it? It's pretty simple. You can do it. Okay, you should have said xy. Anytime you write an equation, start with xy. And then this is kind of weird. 1 comma 2 becomes 1, 2 in a vector. And then this isn't the vector that's actually going anywhere. That's why we call this other one a direction vector. Because that's telling us what direction to go. This is just telling us a start. Start here and go this direction. We're going to go 4 and then 1. Raise your hand if you had that one right. Awesome. See, that's all there is to it. Now let's do one where it's going like down and to the left instead of always up and the right. So what if we had one that started here and goes like that? Would you please remember the equation for that one? In case you're having trouble seeing where that is and counting the little thingies, it's -2 comma -3. And it's going down 3 and over 1. Just negatives running all over the place. I'd say negatives by themselves have caused more grade destruction than any other little line. Negatives are obviously a big deal in every math class, but so still start with xy. Still start with a starting point, which was -2, -3. So nothing's really changed so far. And I'm still saying plus. Note that. Still plus. Still a lambda. And it's still going somewhere. It's just going to the left 1 and down 3. Raise your hand if you had the same thing as I did. Awesome. Now let me show you how we can make this move to the next level. Like, what can we do next? Next, we can take this and let's see if you recognize a blast from the recent past. So -1 times lambda. You remember when you had an x equation and then you had a y equation? Now plus -3 lambda, that's kind of dumb, right? Shouldn't I just call that -3 lambda? Plus a -3 lambda would be the same as -3 lambda. What? Parametrics just intruded into your vectors. Are you seeing the harmony between those two systems of math? It's like old school music, like, I don't know. Who was one of the most famous in the Rat Pack? He was not in the Rat Pack. In the Rat Pack. No, the Rat Pack. Dean Martin and who else? Who is probably the most famous is saying New York, New York. Frank Sinatra. So you take Frank Sinatra and you have Ariana Grande singing a Frank Sinatra song. Like brings the two together. Sometimes they're a bad mix. Okay, anyway. Did Tony Bennett sing with Lady Gaga? Really? Interesting. All right. So, but wait, there's more. I'm going to now solve these and get rid of the lambda. Does that sound familiar? And I'll only have x's and y's left. Admit it, you're excited. I'm so pumped, Mr. Server. Y plus 3 over negative 3 equals lambda. And I've got them both solved for lambda. And then I can set them equal to each other. This equals that. Look, Mom, no lambdas anymore. And I've got it back to rectangular. Except we even have a new name for rectangular. What? It's called Cartesian. I know. So much so fast. But you're growing up. So what your parents say about you. Seems like just yesterday you were a little kid. Now you're all grown up. You want to borrow the car. Go to the parties. All right. We have taken a vector, turned it into a parametric, and then turned it into Cartesian. It's not really Cartesian until I put these together into one big equation, and I'll do that. I'll slide the screen up a little bit and do that. That's going to say x plus 2 over negative 1 is equal to y plus 3 over negative 3. And really, if I wanted to take a long time, I would solve this thing for y, but we don't have to do that. It's got only x's and y's, right? Now, one problem with that, it would create a line that would go forever in both directions. Is this a line that goes forever in both directions? No, it starts here and it ends there. So technically, we'd have domain issues we'd have to deal with, but the domain would just simply be, what's the x value where it started? What's the x value where it stopped? So it's not that hard. But we're not going to really focus in on the domain right now. I'm going to show you this one because I want to have nice completion to it. Do you get, if this really is going to be a line that starts at x equals negative 2, then I could say x has to go between negative 2 and what's the other end of it? Well, x has to equal, at this spot, x is negative 1, 2, 3, negative 3, comma, this spot right here is negative 3, comma, negative 1, 2, 3, 4, 5, 6. It's gone from here to here, and wait a minute, I'm about to, and I hope you realize, do you get that I just did that backwards? All right. So x has to be between negative 3 and negative 2 inclusive. It does touch on both ends. But don't worry, we're not going to really be talking about the domains that much. We're just going to do a whole lot of this. Here's an equation. What does it mean? First of all, what kind of equation is it? Is that Cartesian? Is it parametric? No, what is it? It's a vector equation. And where does it start? At 1, comma 2. And where does it go? 3 to the left and up 4. That's actually one of the easiest forms of the equation. But then, of course, we're going to ask you to convert it. So everybody right now, take that one, convert it to parametric. Take this vector equation and convert it to a parametric equation. If you were off doing other things, come back now. You don't want to be too lost. Try to learn this yourself this weekend. Good luck with that. Unless you listen to this video this weekend. Kind of sad because you're here. You can get it live and in person. Live performances are always so much more expensive. Like the last time I went to the Ariana concert. Yes, a lot of Ariana references is because there's a math behind it coming soon. She wrote a song for me. No, I'm not getting a ponytail. There you go. Raise your hand if you had that one right. That's all there is to it. These are easy peasy. And then, what if, wait a minute, don't these usually have domains? Yep, and the domain is always, remember how you get to pick it? This is the kind where you get to pick it. And you'd say it's between 0 and 1. And actually, if you don't use 0 and 1, you'd have to change these equations, which, why would you want to do that? So always pick between 0 and 1. Because when I put in 0, what happens? That goes away, that cancels, and it's 1, comma 2. The starting point. Right? And what if I put in 1? What do you think happens? I'm going to put a 1 here and a 1 here. Look, it turned into the ending point. Now, that's not, the ending point isn't one of my things I can see here, but I know that when I'll put in a 1, it's going to go to the end of my vector, and it's going to stop there. So it would tell me what points I'm at. Okay, so there's the vector changing to parametric. Now just take it one more step and change it to Cartesian. So solve them for what? Solve it for lambda, and then set your lambdas equal. Okay, so I'm subtracting 1, x minus 1, dividing by -3. Lambda equals x minus 1 divided by -3. Got that one? Now let's do the other one. Y minus 2 equals 4 lambda. Divide by 4. Divide by 4. Funny looking lambda. Lambda is y over 2 divided by 4. Set them both equal. X minus 1 over -3 must equal y minus 2 over 4, because lambda equals lambda, of course. We all know that. So then this must be true. But the danger is that would be a line that would go forever. And so just a reminder, this is not a line that goes forever. All right, so anyway, enough about that. Yay, you're done with that. Now I get to teach you another completely different concept. And this one is called the angle between two vectors. Do you remember I gave you a preview that we were going to learn this? Okay. Would you agree that the angle between these two vectors, the way I'm holding them up in the room right now, is making a right angle? Do you get that I could make a vector for that using, like, 1, 6, 4, or I could even make an equation like I just gave you there and make this vector. And I could make another vector that would be completely separate, that would be like this. But I put them together, they make, gentlemen, they make two vectors that make a right angle. All right. There's a formula for that. You ready? You should be. It's A, B, and I'm leave a little room in between them. A, B, cosine theta. Now I'm going to show you. Did you get that? That's pretty simple. A, B, cosine theta. Now there's more to it. A lot more to it. I'm going to put the word dot in between these two. Do you know why I don't want to put a dot symbol? Because they think it was multiplication, but it's not. It's called a dot product. A dot B is equal to, wait a minute, I'm putting those absolute value bars around those. That makes them into the what's of A and B. Magnitudes of A and B. All times cosine of theta, the angle. Think about it. If here is a vector, and here is a vector, do you get, there'd be an angle between those two vectors. And you might be thinking, but what if they aren't even touching each other? You know what I mean? Like, what if this one's over there? Do you remember that you can move vectors around if you want to? As long as they keep the same magnitude, which means same size, and same direction. Well, I can take this guy and move him over here. We can make the vectors touch each other like that, and then they'll always have an angle between them. So even if, you can't see this at home, but I'm holding up a vector over here, and I'm holding up a vector over here, they aren't touching right now. How can they make an angle? Just move them until they touch. And where would be the logical place to make them touch? At the origin up here, maybe? See what I'm saying? I can move both of them, so might as well move them so that their tails touch. Okay, so when we were adding vectors, we always did a head to tail. This is always tail to tail. Okay, so now let's try it with some actual vectors. And the really cool thing is this will work even in 3D. Like, you've always done angles before where they were always just in the two-dimensional plane, like this. What's the angle between these two? And like, oh, it's 60 degrees. Now, these can be like all kinds of weird angles, but they'll always still, let's say it's like that. I'm trying to make like a 45-degree angle, but it could be like this in 3D space, and this still work. All right, so let's keep the numbers super simple. Let's say A is 1, 2, 3. It's as easy as 1, 2, 3. We'll make B do, re, and mi. No, can't do that. We can make B, how about 4, 5? We got to have one number, -6. So let's find the angle between those two. I'm telling you, it's not going to work out nice. It's not like, surprise, it's a 90-degree angle. It's going to be a weird angle. And one more thing, it's going to be in radians. So what if the angle comes out to 1.6? What does that mean? 1.6 radians. And remember, a radian's about 60 degrees, a little more or a little less? Which one was it? A little less. So like, what if it was like 1.1 radians? Then that means a tiny bit more than 1 radian, which is about 60 degrees-ish. See what I'm saying? So if we get an answer of 1.1, it's not going to be as satisfying as if it came out in degrees, like, oh, it's 23 degrees. All right, you will need a calculator for this one. Everybody grab a calculator. Make sure it's in radian mode, which would be normally the default, but frankly, most of you carry it around in degree mode right now, which I understand. In fact, until you're awesome at this, I encourage you to keep your calculator at degree mode. But now, by putting it in radians mode right now, you will be remembering that, yeah, I'm in radians mode. Need one? Come on up. Just give me some collateral. There you go. Hey, if I took these two things those guys left up here for collateral, and I like smashed them, what would that make? Collateral damage. Okay. All right. So we're going to take A dot B. It's so easy. This part, painfully easy. I'm going to put these guys together. Wait. I'm going to move this. How about it? This will move. Maybe the one will move nicer than the other. All right. Fine. There. And then this one will move. There we go. If I put these right next to each other, I'd like to kind of get rid of the A, so I'll just delete that A. I'm going to use my surgical eraser. It's really small and careful. There we go. Okay. And now, scalpel, please. I'm about to perform the dot product. See if you figure out what I get. What just happened? Okay, there's an extra smudge on the screen. It's just a smudge. Okay, 4 times 1, 4. 5 times 2, 10. Okay, fine. -18, put them all together, -4. Now, like, what is it? What does it mean? All right. I can tell you that the dot product is just a means to an end. You don't really use it for much, except to figure out the angle between two vectors. Do you remember back to matrices when you were in honors higher algebra? There was a thing called a determinant. The determinant wasn't good for much, except in figuring out the inverse. I know right now I just said something like, and purple is why you can never paint your house horse. Like, what? What did you even talk? What did you even say right there? I know most of you don't remember determinants or matrices or even what an inverse of a matrix was. But the point is, this dot product thing, you can't use it for much except in the middle of this equation. Okay, so don't think of this as, oh, so you can multiply matrices? No, this isn't multiplying matrices. If you're going to multiply vertices, or sorry, vectors, there we go. So you can multiply vectors? No, not really. This is not multiplying vectors. This is doing a special thing called the dot product. Excuse me, gentlemen. Try to focus. What? Okay. All right, that goes in your pocket. Thank you. Good. So this dot product, what do I do with it? I go back up to the equation I had in the first place, and that's the dot product of my two vectors, and I put it there. The only thing I can tell you about a dot product that's kind of handy to know, it is if the dot product is ever 0, it's perpendicular. This might be dumb, but it might help you remember it. If I said A dot B, couldn't I make my dot like kind of big like that and almost like the P in perpendicular? If the dot product ever ends up being 0, they are perpendicular. If the dot product ever comes out to 0, then they're perpendicular. Were my two vectors perpendicular? No, because they came out with a dot product of -4. So I know that they're not perpendicular. Okay, so -4 equals, and next we got to do magnitude of A. All right, which one was A? That's this black one here, 1, 2, 3. Do you remember how we do that? Square root of, come on, you can do this, 1 squared, 2 squared, and 3 squared. Think that's square root of 14? Okay, excellent. Now we'll do magnitude of B. Here's our B vector. Magnitude of that one. This is times in between them. Times, not dot. That's important to know. Times square root of, and again, this is 4 squared, 5 squared, and 6 squared. So the negative will cancel when you in the squaring process. So it's going to be 16, 25, and 36. 77. And then cosine theta. And wasn't this all to do something? It was to find an angle. Do you get you can now solve for cosine and then do inverse cosine? And you'll have the angle. This is why you have your calculator out. All right, so everybody right now, divide both sides by root 14 and root 77. There's no reason we need to put them together right now. Okay. So cosine theta equals this. Do you get we're going to do inverse cosine to get rid of the cosine? And we're going to do inverse cosine of this, and we'll have the angle. I'm going to pause for a second. We'll pull up the calculator. Okay, so now I'm ready to put this in the calc. And I'm going to put this in, and I'm going to do inverse cosine of that. Okay? So I'm going to start right off with inverse cosine. And that is right above the cosine. So there we go. There's the inverse cosine of what? -4. Just make sure I'm using the negative key, not the minus key. Divided by, and just to be safe, whenever there's like a couple things, I like to put a parentheses. So I'm going to put parentheses, square root of 14. And then get out of those parentheses and with an arrow and then say times the square root of 77. Get out of the parentheses and then put in end parentheses to end the whole thing. And then I'm going to hit enter. Cool, 1.69. Did I happen to have an angle of 1.69 degrees? Is that humanly possible? Yes, but remember, I'm probably in radians, right? Okay, so I'm going to go and check that and make sure. Mode, I'm in radians. Yep, see right there? So I'm in radian mode, so that means my answer right there was 1.69 radians. Nothing wrong with having an answer that's in radians. But just so you know, if you wanted to know how many degrees it would be, it's about 58 degrees for each 1 radian. Okay, so if I took this and times by, I have 58 is not exact. I'm rounding here, but I know some of you like degrees better. Ooh, it's about a 98-degree angle between those two vectors. 98 degrees, a little open, a little bit more than a normal 90-degree angle. All right. I want to give you another one with nice, easy numbers. And let's see if you can, with a nice, clean slate, First of all, write out that formula that started A equals A cosine theta. Write it out, except it wasn't just A. Write out that formula. Don't just look at your old formula. That's not going to help you remember it. The physical act of writing out this formula is going to help you remember it. You'll need it. Did you realize it was A dot B equals magnitude A, magnitude B, cosine theta? Raise your hand if you got the formula right. Awesome. Now, would it be possible for me to tell you the angle between the two? What if I, just for a moment, what if I told you the angle was 90 degrees? Think about what I said about the dot product. If this is 0 and this is 90, do you get it doesn't even matter what these two were? Why? Because it must be something special about cosine of 90. What's the cosine of 90? 0. That's why if we ever have a 90-degree angle, we're going to be doing cosine of 90, and cosine of 90 is 0. In case that's not like processing for you, here's 90. Remember how we did these? It would be like, oh, that's 0, 1. And what's cosine of it? Oh, it's 0. So cosine of 90 is 0. Gives you the dot product of 0. Okay, cool. Just a little side note there on that whole like 90-degree. One more thing about if they make a 90-degree angle, do you get that that makes the two vectors perpendicular? You see what I'm saying? If they make a 90-degree angle, they are perpendicular. So if they ever talk about, oh, by the way, the vectors are perpendicular, they're saying that the vectors have a 90-degree angle, which means that the dot product would be 0. Okay? So by saying one little thing, they're telling you a lot. Reminds me of that past homework problem where we said like, oh, x equals I, by the way. And you were like, oh, so that means if it has one root of I, then the factor would be x minus I, and then there must be an x plus I, and then you can put it all together and say that it kind of leads you down a path, right? As soon as I say that they are perpendicular, it leads you down a path. You go, if they're perpendicular, then the angle must be 90. If the angle's 90, the dot product is 0, and then you can use that to solve parts of the problem. Okay, so now I'm going to give you two vectors. And I want you to tell me the angle between these two vectors. -1, 1, 0 is going to be our A vector. Our B vector is going to be 1, 1, 2. Would you please figure out what would the angle be between these two guys? It'll take you a moment. You'll have to do magnitudes. You'll have to do dot products. You'll have to do an inverse cosine. But when it's all done, you'll have the angle between the two vectors. I'll pause for a second while you give that a try. Okay, let's see if you figured this out. Dot product, super simple. I'm just putting them side by side. 1, 1, 2, and you go this times this, -1, +1, 0. Add them up, 0. Boom! What just happened? Dot product is 0. What do you know? They're perpendicular. What's the angle between them then? 90. Done. Oh! Isn't that awesome? Okay. Does it usually work out that nice? Pretty much never. What was the probability that that was going to happen if I just picked random numbers? Well, there's 360 degrees that this could have come out, right? Well, except that it can't even really be 360. There's a million different angles that could have been. That was a 1 in 360 degree chance that that's the angle between them. Although, wait a minute. Wouldn't it always be 90 or less? How about inverse cosine? Do you remember inverse cosine? Okay, maybe not 90 or less. What's the rules on inverse cosine? There we go. You remember trig. You remember circle trig. Inverse cosine is only allowed up here, and so therefore it could go between 0 and pi, and so therefore 0 to 180 is the, like, once it went past 180, we'd say instead of like 181, we'd say, oh, it was 179. See what I'm saying? If it was going to be 180, and then it was going to open one more degree past 180, boop, then we start measuring the angle on the other side, and we'd say it's 179 instead of 181. That makes sense? You're right. That's what I'm trying to say, is we can't go to 181, so as soon as it would seem like you would get a 181 angle, you're going to measure the other direction, and you'd have a 179. Okay, stop. I need to move on. So you got the angle between these two, but this one did work out really nice. In fact, a little too nice. You need to see one where it doesn't work out that nice. But let's do that on your homework. All right? So I'll show you which problem we want to do together on the homework. Yes. Well, let me get them moving to the right place while you ask this question. Everybody find the homework from yesterday, and we're going to go add a few problems beyond where I assigned. Okay? So go to last night's homework. And no, this is not a trap. I'm not going to ask you to grade last night's homework right this second. We're just going to add some problems to it. But boy, that would be a good one to grade then after we'd spent 2 nights on it, wouldn't it? I'm going to pause for a second while you find last night's homework. All right, so we're going to start here. Notice it says find the angle between these pairs of vectors, giving the answer in degrees. Oh, I just told you to do it in radians. Yeah, it's all right. It's the same exact thing except do it in degrees. You got to follow the directions. I was expecting it to go with radians because we usually do that in the test, but and just do whatever it says in the directions. All right, so back to what is this vector? You were used to seeing them like this, -4, -4. You know what I mean? What about this vector? -3, 2. And if I want the angle between those two vectors, anybody remember a formula? AB equals AB cosine theta. But it's more complicated than that, so let's go back, and this is A dot B, and this is magnitude. Got it so far? All right, did they ever tell me the angle? No. So at the end, I'm going to find the angle with the inverse cosine. So all I got to do is find this magnitude. That's easy. Magnitude of A. That squared. So square root of 16 and 16 squared to 32. Yes, it simplifies a little bit, but that's usually we're going to do a decimal anyway in the calculator in a minute. And then the B, that squared, 9, 4, square root of 9 and 4, square root of 13. And then what's A dot B? Well, let's go this times this times that, add them together. Positive 12, negative 8. Add them together. Positive 12, negative 8. Pretty sure that's 4. Can anybody verify that they had 4 before I said it? Okay, good. So 4 equals root 32, root 13 cosine theta. And I know that looks really messy, but you just have to divide both sides by the square roots there and take inverse cosine. So this is 4 over square root of 32, square root of 13 equals cosine theta. And then you do inverse cosine, and you'll have your decimal. Okay. Your homework for tonight is to add these two, this page, just this page, this one page of problems. Whole page? Yes, you're adding a whole page to last night's homework. And then we have to get to the new page and do a couple of those. Yes, you can handle this. It's not that bad. On the new one, it's this one. We're going to do page 1. And let me see which one I like better. 1 and 2. It's page 1 and 2. So last night's homework, you're adding that page with the little Google symbols. And tonight's homework, you're just going to do pages 1 and 2. The only thing I haven't taught you so far, I want to make sure I don't leave any gaps for you. What if I said it starts here and it goes to here? Well, didn't I tell you where to start? Yeah, let's say it starts at 4, 4. And it goes to there. Do you get, I've really told you a vector? If I told you it goes to there. And let's say this other spot is at 8, 7. Well, then it went up 4 and up 3. So that would be like this. It went 4 in the I direction and 3 in the J direction. So if I give you 2 points, I've really told you a point to start at and a direction to go. Direction vector. There. Now you know everything. Okay, and that was a little intense. All of that page. Okay, to clarify what tonight's homework is, you're adding one page to last night's homework, which is the page with the little Google symbols, and you're doing the first 2 pages of the new assignment. The first 2 pages of the new assignment. And that's all I have for you for today.